Okay, my name is Jeff Harvey. I'm from MMA Design out of Boulder, Colorado. We've been working for about 3 years now on solar arrays, deployable solar arrays for CubeSats. So what I'm going to do is talk about what we've got here. If I can figure these buttons out. This is just MMA, the kind of stuff that we do, so I'll skip that. 3 years ago, pretty much most of the solar arrays for 3U CubeSats were just flip-out panels that kind of, on the sides, they would store them on the side with a simple pivot hinge and a launch restraint for the old P-pod spec. At that time, there was a desirement from a lot of guys out east for more power, potentially, to try to do military applications for CubeSats. What we did at MMA is we took a look at it and we said, well, you know, how would you store a solar array very effectively with a gimbal on it for applications where particularly you wanted to point nadir with the long axis of your spacecraft. So we came up with the Hawk Solar Array. Essentially what we did is, the main thing was that we have a 6.5 millimeter thick gimbal for single axis tracking, and then on the long axis you could rotate the spacecraft. And then we fit in the 6.5 millimeter that's external to the basic P-pod volume. It turns out that this design is also very applicable as you get, if you want to go to a 6U where you use the entire 20 centimeter face, you can just basically take it double the dimensions of the wing. So we came up with the Hawk. It was funded by Air Force Research Labs out of Kirtland. And the background of our company is that we're all ultra high reliability spacecraft solar array systems and mechanical systems type. So what we did is we attempted to use all the basic methodologies that we had used on very high-end spacecraft, both for NASA and DoD, and apply them to a very cost-effective solar array system. So we used very similar materials. We didn't use, at the time, people tended to use G10 for the base substrate material. We used graphite with, 15 million PSI modulus, things like that. What we did is we also made it so it was extremely modular. That was a fundamental feature that we were looking for, is that it seemed like many applications, the CubeSats were changing very rapidly and continue to change. So what we did is, as you can see in this lower graphic here, you can use it with a gimbal. You can use 1 panel, 2 panels, 3 panels, up to 6. When you get all the way to the right side of the chart, that shows 5. Our current arrangement is really to have 3 double panels on there, so we're equivalent of 6 wide. When you get to a 6U spacecraft, which actually we just did random vibration testing for the second time using the ESPA-RUG vibe spectra, and just are in the process of flight qualifying what we call EHawk, which is essentially twice the power of this one. This one does 36 watts peak power on the left when you have the single axis gimbal. When you get all the way to the right side, where you're using a 6U, many more panels, we're looking at 72 watts. That's EOL, or BOL rather, power. So that's with all the knockdowns on the cells and running at 70 degrees C assumed. The basic system is shown here. Essentially, you've got 2 panels. They flip out, very conventional system. There's a common axis through the gimbal sitting in that little space at the very top there. And so you can rotate the panels as shown about the axis there. Essentially, the entire system, including the gimbal, is 0.6 kilograms. We're pulling about 140 watts per kilogram on the real hardware, though we show 130 here. The deployment sequence is pretty simple. It's a trifold. It's also a trifold on a 6U where you're making it 20 centimeters wide instead of 10 centimeters wide. Using UTJ cells. Essentially what they do is they come out like in the left here, you're stowed on the face. We actually run our load paths quite differently from other solar arrays where you tend to have a simple cantilever, or not a cantilever, but a root pin, a pin at the 2/3 point, and then you let it vibe that way. What we do is we have a cage around the entire system, so when you melt a wire, the system moves down, cutting your load paths less than half, which is just a more efficient structural system with a little bit more complicated device for the launch restraint, which has been flight qualified. Everything I'm showing you, I apologize, we don't have real pictures here. We're flight qualified for ORS squared. We're actually going out of Walter's deployer. And on that mission, with this configuration that's shown on the right here, and I have real pictures actually later in this of the latest stuff, plus we have the 6U version of this, which is up to 72 watts BOL. Here's some pictures of it, and making sure you guys see what I see. We configured it for the 6U. Actually, the center picture here is the way it is on ORS squared. That was originally meant to be more of a conventional 20 centimeter by 10 centimeter by 32 centimeter vehicle, but it worked just fine on the larger planetary systems unit. We fit in the 6.5 centimeter or millimeter space on the edges, so it doesn't use very much volume. It's extremely high watts per cubic meter type system. Again, what we were going for in the whole thing was to have a very effective system that's high performance. You can see it's stored in the upper right-hand corner, sitting on the face where it slides inside the P-pod in that application. In the lower right is the 6.5 millimeter gimbal. That gimbal uses a wrap wire inside of it, not slip rings, so you can rotate 180, then you have to come back and keep it centered that way. This is the proto-flight unit that we delivered that's presently at AFRL, I believe right now is the current location. It's been going between Ames and AFRL. It's fully flight qualified, full vibe, full thermal testing, reverse bias testing to make sure we get the performance. That one was actually hit with about 65 Gs peak quasi-static load per the high spikes that you start seeing inside of a P-pod. So it's a TRL-8 version. We expect it to be flying, I believe, late spring of 2014 is the current. One of the things that we also did with the solar array is we have a very high first mode. We advertise 1.5 hertz first mode. The finite element model shows that it actually being over 2.5 hertz. Becomes really important if you're going to do any imaging, which you guys have been talking about on and off throughout yesterday, because you don't want to, you want to have a well understood spacecraft deployables dynamic interaction between the two, so that's really important. We also have welded interconnects at notes here with the UTJ spectral lab cells. Again, they're sitting on a vibration table, getting ready to be shaken over a ball and boulder, and it's ready to go. And like I said, we have the next version of this, which is twice the size, twice the width, and actually is scalable up to about 140 watts on the 6U. You have to use a little more of the volume on the outer face when you start getting that large. One of the notable things between the Hawk, which is completely flight qualified TRL-8, and the eHawk, which is funded by AFRL also under phase 1, phase 2s, is that we have a morphing structure in eHawk to keep the frequency up high. One of the fundamental things that we're doing with these is to make sure we have a well understood dynamic system. So in conclusion, we're pulling over 130 watts per kilogram. That is extremely good performance by any solar array standards. Our peak power for the 3U version is 36 watts. You can go up to 140 watts if you go to a 6U. With the baseline 6U, we're presently getting ready to flight qualify fully is 72 watts. And again, those are beginning of life with the appropriate knockdowns running at 70 degrees C. For some of the lunar applications, I've looked at it, and you get a few more watts due to the, it looks like they probably run quite a bit cooler than a LEO mission. And of course, we sun track and it's efficient. So that's pretty much, I wish I could show you guys pictures of real eHawk hardware. This is what the Air Force said we could show as of right now. So we had another pitch we had to yank yesterday. Any questions?
So the current design is single axis. Do you have any?
Correct.
Do you have any design that has?
We actually have a second axis. The original eHawk work, when we first started it, the whole idea was to do a second axis. We actually designed a gimbal for that too. And we did not carry that to flight qual level. Primarily because we've had very little customer interest in it, and it takes up a portion of the top U, where we've been trying to stay completely out of the basic envelope of the CubeSat. But yeah, we do have one. We have a design. It's been, it was prototyped and built, but it wasn't, tested in the relevant environments and stuff.
So the 6.5 millimeter thickness would be.
That's, if you look at the P-pod specification, there's a space, there's the rails, and around the space there's a 6.5 millimeter tall area that you can, it isn't accounted for in the basic description of a CubeSat. So you can slide this entire solar, including the gimbal, all fits in those volumes. There's one on the top, one on the bottom, one on all four sides, 6.5 millimeters.
It would be a lot more than that.
The second axis has to go down inside the, yeah, exactly.
We'd be interested in 2 axes, actually.
Okay.
Potential customers. Because a lot of deep space customers probably would be. So are there things you can share about what you think will be the operational life in deep space, temperature range, radiation dosage, things like that?
We spent a bit of time thinking about, for deep space missions where they get, you get pretty cold, the initial thermal modeling I've done is, as long as you're not going into the shade of the moon, for instance.
For how long?
Well, we didn't even go there. We just kind of looked at it and said it's going to get very cold. So I haven't looked at that yet. I think you'd be at minus 100 degrees C. We have experience at looking at extremely low temperatures in systems, and there's nothing in our system that is particularly, with the exception of the gimbal. The gimbal starts having issues, and we'd have to study that, but it also has a lot more thermal mass. Typically, the wings of a solar array, particularly the way our system works, is our panels are only about 30,000 7-inch thick graphite, and I actually have holes in the backsides of the cells to radiate out the backside as well as reduce mass. Probably in the lunar environment, you would want to not put the ports behind the hole in the backside of each cell, just because it doesn't make a huge difference in specific performance. But it's a fundamental parameter that we use to weigh how good the solar array is its specific performance in watts per kilogram. So that is one feature you could leave out, and of course it also helps you with radiation. And yesterday there was some discussion about which I took massive notes on. What the radiation environment is. What I did is I took it and I ran it out for a 2-year mission, and I was playing with it out at Geo, and things are not. We were using 5 mil cover glass, for instance, in our kicks for ourselves, and it seems like the degradation is not too awful. In fact, I think it's probably set off by running cooler than running at LEO, because when you look at your knockdowns for BOL calculations between what your theoretical performance of your solar cell would be versus the actual manufactured, the knockdowns for welding, the knockdowns, things like that you get for micrometeoroids, a lot of the things that knock you down in LEO don't knock you down when you're away from the Earth.
Okay.
So I think my initial thought was we were probably starting to push 40 watts potentially when we were in more of your environment for a 2-year mission, but that's just preliminary numbers.
Right. Well, that would be adequate for our application.
Yeah. When you get to the larger, the EHawk, which we're really we're working. What we're doing is we're at the stage now of our program where we're trying to make this very cost effective, and we just got funded last week by the Air Force to make several of these to reduce cost. I have to stop talking. Okay.
Thank you.
We got funded, yeah, so to do transition funding, which is to turn it into a manufacturable system versus what you come up with on an SBIR.
For this community, electric propulsion is no doubt very enabling to get to the moon from, say, GEO. And towards that end, if you could be expansive, what do you think the most power you could deliver in a 6U to them to support their electric propulsion?
Well, assuming I can get some of the envelope out of the spacecraft, 140 watts is pretty easy to do. You could probably, if you were willing to give a couple of centimeters on the face of the spacecraft, you could probably double that.
So you could get to...
Structurally, you could double it.
Okay, so if they allocate some of their volume for a larger array, they could reasonably expect to get almost 300 watts.
Conceivably,
in a 6U.
Assuming the GLOs stay low and make it controllable dynamically. kind of goes back to the discussion you and I had at AFRL that time, where I get uptight about the dynamic interaction of the propulsion system and the deployable structure, which is the solar array in this case. But yeah, I don't see why the morphing capability for the 6U, what we call EHawk, essentially what we do is we take a flat panel and we pop it into a V. It changes the moment of inertia of the structure by a factor of more than an order of magnitude. So it makes it really strong and really stiff, which is really important for what you guys are trying to do, I think, on a lot of the applications.
Okay. Don? Thank you very, very much.
Okay.